Okay, this video begins Unit 3, Stoichiometry, and I must start the video by saying you need to follow whatever rule your particular teacher has given you with regard to rounding molar masses or atomic masses from the periodic table. In my class, I have my students round their molar masses off to the tens place. If your teacher has given you some other place to round to or asked you to carry all the digits when you take masses from the periodic table, then you should follow whatever rule they have given you. However, in this set of videos, I will have them rounded off to the tenths place to match what I've told my students. So first, before we get to the mathematics, let's talk about the mole. And the definition of the mole mathematically is the number of particles that are found. The definition of a mole. Mathematically, the mole is defined as the number of particles in 1 mole. 6.022 times 10 to the 23rd particles is equal to 1 mole of any substance. It's named in honor of Amedeo Avogadro, and it's often referred to as Avogadro's number. Now, with this idea of particles, please understand there's a variety of particles that can fit this. So far this year, what we have covered is the particle might be a molecule, the particle might be an individual atom, the particle might be a formula unit, and last, the particle might be an ion. How do you know the difference between all of these? You have to go back to the original definitions of what each one of these terms means. A molecule means a single unit of a covalently bonded substance, which means it will be made up of totally nonmetals. An individual atom is an individual atom of an element, elements as found on the periodic table. A formula unit is the smallest unit of an ionic compound, so it's going to be made of a positive ion, cation, and a negative ion, anion. That can be both monatomic ions, single element ions, or polyatomic ions, like sulfate, for example, SO4 negative 2. If you're counting the individual ions and you're looking for how many ions of that particular ion type is found in an overall formula unit. So now let's see if we can put this into practice, starting with number 19. Number 19 says calculate the following quantities, and we're going to go through A, B, and C here on number 19. Starting with letter A, how many nitrate ions are there in 2.5 moles of aluminum nitrate? Step 1 is you first need to know what aluminum nitrate is. So aluminum is Al plus 3 according to its location on the periodic table, and nitrate is a polyatomic ion, NO3 negative 1, which can be found in your ions list and was one of the ones we memorized earlier in the fall. And then the next step would be the crisscross method is going to give you the overall formula for this. So the 3 on the aluminum is going to come down and become the subscript on the nitrate, and the 1 becomes the subscript on the aluminum. So the overall chemical formula for aluminum nitrate will be AlNO3 parentheses 3. And now we're ready to solve the actual problem. So starting with 2.5 moles of aluminum nitrate, step 1 is going to be convert from moles to formula units because aluminum nitrate is an ionic compound. So just as we talked about in the definition of a mole, 1 mole of aluminum nitrate will be equal to 6.022 times 10 to the 23rd formula units of aluminum nitrate. And the key in this particular question is to realize that you're not yet finished, because the next step is to convert from formula units of nitrate to ions of nitrate. So for every 1 formula unit of aluminum nitrate, let's see if I can squeeze this in, AlNO3, there are actually 3 ions of nitrate. So when you look at the chemical formula for aluminum nitrate, we're actually identifying how many ions there are in that formula, and there are a total of 3. So now it's just a matter of doing the calculator work. 2.5 moles times 6.022 times 10 to the 23rd times 3 ions, and I'm going to squeeze this answer down below. Obeying significant figures comes out to 4.52 times 10 to the 24th ions, NO3 negative 1. And on to the next one. How many moles of CO2 are there in a 450 gram sample of CO2? And take note, there's a decimal point at the end of that 450, thus indicating that 0 is not a placeholder, but is actually a significant figure. So there's 3 significant figures in 450 in this particular case. So step 1 in this particular problem is going to be to convert from grams to moles, and you have to know that the conversion factor that's necessary here is that 1 mole of any substance is equal to the molar mass of that substance. So in adding up the molar mass of carbon dioxide, you'll get a total of 44.0 grams CO2. And again, that's 1 carbon at 12.0 apiece, 2 oxygens at 16.0 apiece adds up to 44. And again, this is an example of what I was talking about. If your teacher has instructed you to carry more digits on your molar masses, then you should do so. And molar mass is always equal to 1 mole of that particular substance. So this will allow us to convert the 450 grams to moles. And this particular question asks for moles. So it's only a single step conversion. And your answer with proper significant figures is 10.2 moles CO2. And last but not least, moving on to letter C, what is the mass of 8.00 times 10 to the 24th formula units of NaCl? So again, we're starting all the way over here to the left with our original number, 8.00 times 10 to the 24th formula units, NaCl, because NaCl is in fact an ionic compound made of sodium and chloride ions, and it wants to know what the mass is. So you have to recognize that mass means grams. So this is going to be a 2-step conversion because we're going to have to convert from formula units to moles and then from moles to grams. So the first conversion factor is Avogadro's number, 6.022 times 10 to the 23rd formula units NaCl for every 1 mole of NaCl. Step 2, 1 mole of NaCl for every 58.5 grams NaCl. 1 sodium plus 1 chlorine equals a total of 777 grams NaCl. And I'm just squeezing the units underneath there because I'm out of space. The correct number of significant figures in this case is 3, because if you go back to your original number, 8.00 has 3 significant figures in it. And that finishes that page. But stoichiometry continues on to the next page with number 20. Number 20 says, what is the percent by mass of hydrogen in ammonium phosphate? So step 1 is going to be to write the chemical formula for ammonium phosphate. So ammonium is NH4 plus 1, and phosphate is PO4 negative 3. Crisscrossing, like we've done before and been doing all year, means this 3 is going to come down and the 1 is going to come down, and our final formula is going to be NH4 parentheses 3 PO4. Remember, when you crisscross, you drop charges, and you should reduce if possible when you're doing ionic formulas. So ammonium phosphate is NH4 parentheses 3 PO4, and it wants to know just the percentage of hydrogen. You can calculate all the elements if you like, but this particular question is asking for hydrogen only. So step 1 is I'm going to determine the total mass of hydrogen in this chemical formula. So I have 4 hydrogens, and then this quantity is times 3. So I actually have a total of 12 hydrogens in the compound. So to calculate the mass of the hydrogen alone, I would have 12 atoms of hydrogen times the mass of hydrogen, which is 1.0, or a total of 12. And when you're doing percent, it's the mass of the individual element over the total mass in the compound. So now to do the total mass in the compound, I'm just going to go straight across element by element and add it up. So in this case, nitrogens, I have 3. So I would have 3 times 14.0 for nitrogen, plus the hydrogen, and again, the hydrogen is 12 times 1.0, plus now the phosphorus. There's only 1 phosphorus, so I'm not going to write the times 1. I'm just going to write the mass of phosphorus, which is 31.0. And last but not least, plus 4 oxygens at 16.0 apiece. And you can honestly do this whole business right here in your calculator, I'm simply writing it out to make sure you're clear on where that number is coming from. And when you do, that's going to come out to 149.0. And again, this falls in the same category. If your teacher has asked you to go more than the tens place, then you should do so. And we're calculating a percent, so the whole thing will be times 100. And when you complete this calculation, it comes out to 8.1% hydrogen. Moving on to number 21. Number 21 is an empirical formula problem. If you remember from the regular part of the semester, empirical formula is a pretty involved process. It has a series of steps. The most important thing in being successful in an empirical formula problem is not leaving out a step. So when you're studying and preparing for your exam on this particular technique, make sure you're practicing saying what those different steps are. The first thing you want to do is write the elements involved down the left-hand side of the paper. So this particular question involves sodium, sulfur, and oxygen. Next, in this question, it tells you the percentages of each of the elements involved. And actually, it only gives you the percentage of sodium and sulfur. The sodium is 29.08%. You are allowed to simply consider that an amount in grams, because if the amount of each substance by percent is the percentage of a 100-gram sample in total, then it is the same as the number of grams. It also gives you the amount of sulfur as 40.57. And then how do we get the amount of oxygen then? Well, percentages must add up to 100. So if you do 100 minus the amount of sodium and the amount of sulfur, you will see that your amount of oxygen is 30.35%. And again, we can immediately consider those the amounts in grams. The first step in an empirical formula problem is to convert from grams to moles. In order to convert from grams to moles, that means you divide each of the amounts in grams by the molar mass of that element. Now, again, I'm going to the tens place with each of mine. You follow the lead of what your teacher has requested. An important thing to note in this, and a common mistake, is when you get to oxygen. Kids often look at that oxygen and go, oh, oxygen's diatomic. Shouldn't that number be 32? The answer is no, because the oxygen isn't by itself in this case. It's actually in a compound with sodium and sulfur. So make sure you're only including the mass of an individual atom of oxygen. So now once you divide each one of these through, that step gives you the number of moles of each of these substances. So the top one, sodium, comes out to 1.2643. Sulfur 1.2639, and the oxygen 1.8969. Now, how many digits you carry out in this honestly is up to you, because your final answer is going to be a chemical formula, and sig figs aren't going to apply. What you want to be careful about is not rounding the numbers off too much. Also, that's why in this particular case, you may want to carry out additional digits on your molar masses as well, rather than rounding them off to 23.0, 32.1, and 16.0. But honestly, that part is up to you as well. So, step 1, grams to moles. Step 2, divide each number of moles by the smallest number of moles of all the options that you get, all the answers you get in this step. And in this particular one, that's going to be 1.2639. So I'm going to divide each one of these by 1.2639. Now I'm going to hit pause here for just a second, and I'm going to go ahead and write in all these next answers. So when you divide each one of these by 1.2639, and again, you're dividing them all by the smallest, they come out to 1, 1, and 1.5. And the common question is, well, I didn't get exactly 1.5, I got 1.499. You have to recognize the common fractions. Who are the common fractions? 1.25, 1.33, 1.5, 0.66, and 0.75. So you have to be able to recognize each one of those decimals corresponds to a fraction. 1/4, 1/3, 1/2, 2/3, and 3/4. When you see any one of those, you should write the number down in decimal form that matches up with that. And then the next piece is, the last step is multiply till whole. In other words, you're going to multiply by the factor that was the denominator of that common fraction in order to get a whole number. So in this particular case, my common fraction is 1/2. So the denominator on 1/2 is 2. So again, the denominator of the fraction half is a 2, so I'm going to multiply each one of these by 2. Now, again, a common mistake is to want to only multiply the 1.5 by 2. But whatever you do to one, you must do to the others, because what you're trying to determine here is a whole number ratio. So we end up with 2, 2, and 3, and so our final answer then for the empirical formula for this particular substance is Na2S2O3, and that's actually your final answer. Next is number 22, illustrates the difference between an empirical formula and a molecular formula problem. So in this particular question, it's telling you the empirical formula of the compound is C2H3, and it wants to know what the molecular formula of the compound would be, knowing that the molecular molar mass is 135 grams per mole. So the method we use for calculating that is the molecular molar mass divided by the empirical molar mass will give you the factor by which to multiply each of the subscripts in the empirical formula to get the molecular formula. A molecular formula and an empirical formula can be the same. In this particular case, the empirical molar mass for C2H3, we're going to have 2 carbons at 12.0 apiece plus 3 hydrogens at 1.0 apiece, and this total adds up to 27.0. So that's our empirical molar mass. So that goes on the bottom of the fraction, and the top of the fraction is the 135 that's provided in the question. And 135 divided by 27 comes out to 5. And this should come out to a whole number or be very, very close to the whole number. And then the process is you take this number times each of the subscripts. So 5 times the subscript on the carbon, which is a 2, becomes carbon 10, 2 times 5, and 5 times the subscript on the empirical formula for the hydrogen, which is a 3, and 3 times 5 is 15. So the molecular formula for this substance is C10H15. The next set of questions are chemical reactions, writing and balancing chemical reactions. For each of these, it's asking you to write the full balanced equation and then identify the type of reaction for each one. So let's go ahead and begin with the first scenario. It says nitrogen gas, so I have to recognize that nitrogen is one of the diatomic elements, so N2, and then the gas symbol, and magnesium metal. Metal indicates that we're talking about a solid. React to form solid magnesium nitride, excuse me. Magnesium is Mg plus 2, nitrogen is N minus 3, so when I crisscross this, I'm going to end up with Mg3, N2, and it told us in the question that it was a solid in the scenario. Last but not least, we need to balance the overall equation. Nitrogen's 2 on the left and 2 on the right. Magnesium's 1 on the left, 3 on the right, so we need a coefficient of 3. What is the reaction type? Synthesis. On the next page, we continue with more chemical equation writing and balancing. So just let me get this focused in here, and we'll continue with number 24. In number 24, we react aqueous silver nitrate and nickel metal to form silver metal and aqueous nickel 3 nitrate. So going through each step at a time, starting with the silver nitrate. Silver is always Ag plus 1, nitrate is NO3 minus 1, and again the scenario told us that it was aqueous. Next, nickel metal. That means Ni solid. React to form silver metal, Ag solid, and both nickel and silver, they're not part of the diatomic 7, so it's important to remember that you're checking we don't miss any that are supposed to be diatomic. And last but not least, nickel 3 nitrate. Nitrate's -1, so it's going to be Ni, and then nickel 3 means the nickel is positive 3, so NiNO3, 3, and it tells you in the question that it's aqueous. Next step is to balance the overall equation, which in this particular case we need a 3 in front of the silver nitrate and a 3 in front of the silver metal. If you go back and forth from left to right, you can see that then gives us 3 silver, 3 nitrate, 3 nitrates, 1 nickel, and 1 nickel. And the reaction type is single replacement. Single replacement when one ion, either a cation or anion, is replacing the cation or the anion in the compound. Double replacement is when you have two compounds and the cation and the anion in each are switching and matching up with the cation and the anion from the other compound. Number 25. Number 25 is solid platinum 4 fluoride. So step 1, platinum 4 means that it was platinum plus 4. Fluorine is F negative 1, so we're going to end up with PTF4. And again, it tells you that it's a solid. And then it says reacts to form, so we're immediately going to our yield sign. And this is how you can conclude that this is a decomposition reaction, because there is only one reactant present in this particular reaction. And then it reacts to form platinum metal. Again, metal means solid, and fluorine gas. Don't forget, diatomic 7, F2, gas. Last but not least, we need to balance the overall equation. Platinum's left to right, 1 and 1. Fluorine's left to right, 4 and 2, so we need a coefficient of a 2 in front of the fluorine. And that finishes number 25. That finishes the reaction writing and balancing, and then the type. The next one, number 26, it starts with part A with you writing the reaction, but the purpose of it in this particular case is for you to build on each one of these scenarios into stoichiometry. So it says write a balanced equation with the smallest whole number coefficients for the reaction of nitrogen gas with hydrogen gas to form ammonia. So nitrogen gas, diatomic 7, N2G, plus hydrogen gas, again, diatomic 7, H2G, to produce ammonia. Ammonia is one that we've covered throughout the year over and over again. It's an example just like water where you need to be familiar with a common name. It doesn't tell you the state of matter on the ammonia, so we're going to leave that blank. It could be a gas, and in this case it is. But because it doesn't tell you in the question, you wouldn't be expected to include it in this particular case, because it's not like a solubility rule situation where you can use solubility rules to predict whether it would be aqueous or solid, for example. So this is one where I'm not going to mark it because I wouldn't hold my kids accountable for being able to remember that that's a gas. So next thing we need to do is balance from left to right. The nitrogens, we have 2 on the left and only 1 on the right, so we need a coefficient of 2 in front of the ammonia. That 2 then impacts the full compound, 2 times 3 for a total of 6 hydrogens, so we need a 3 on the left-hand side in front of the hydrogen. Now we can use this equation to calculate different relationships between the substances in the balanced equation, which is the whole premise behind the idea of stoichiometry. So in letter B, it says how many moles of ammonia are formed when 1.34 moles of nitrogen react. So 1.34 moles of nitrogen is our given, and you must fully label this. So we have 1.34 moles N2, and we're trying to calculate the moles of ammonia. So now, moles of nitrogen, 1 mole N2 for every 2 moles NH3. How do I know that? Those are the coefficients from my balanced equation. So if you jump back up here to the equation, you can see there's a 2 in front of ammonia and nothing in front of the N2, which means a coefficient of 1. So up at the top, those coefficients are the values that we use in the moles over moles step when doing a stoichiometric calculation. Anything else, the number of moles is always 1. So in other words, when you're doing moles related to molar mass, moles related to Avogadro's number, the number of moles is 1. When you're doing moles compared to moles of another substance in an equation, the balancing coefficients are your relationships. So as we multiply across there and apply sig figs, our final answer should be 2.68 moles NH3. Moving on to letter C. How many grams of hydrogen are required to produce 2.75 times 10 to the third grams of ammonia? And I'm going to start as far over here as I can, guys, but it's going to be tight for me to fit this one in the space provided because of the numbers in scientific notation. So we'll do our best here. 2.75 times 10 to the third grams NH3. And again, it wants to know the number of grams of hydrogen. So step 1 is I'm going to have to convert the ammonia from grams to moles. And this is an example where the number of grams from the periodic table, the molar mass, which is 17, 1 nitrogen and 3 hydrogens, relates back to 1, whoops, I wrote NH4 there, sorry, let me fix that, relates back to 1 mole. So this is the situation where the number of moles is not the coefficient when you're comparing it to molar mass. So 17 grams of NH3 is equal to 1 mole of NH3. Now the next step is where we are using the coefficients because we're converting from NH3 to H2. So 2 moles of NH3, coefficient from the balanced equation, for every 3 moles of H2. Again, coefficient from the balanced equation. And last but not least, we're converting from moles to grams, but now we're talking about hydrogen gas. So 1 mole of H2 is equal to 2.0 grams of H2 from the periodic table. 2 hydrogens at 1.0 apiece. Multiplying and dividing across the whole dimensional analysis, we end up with 485 grams of H2 when we apply significant figures. And that now finishes number 26 on that page. 1 to go in the stoichiometry section, which is number 27 at the top of page 9. So number 27 at the top of page 9 gives you an unbalanced equation first. So step 1 is we're going to go through the balancing of this particular equation, which is a combustion reaction of propane, C3H8, with oxygen to form carbon dioxide and water. So working from left to right, on the left-hand side we have 3 carbons. When we come to the right-hand side, that means we're going to need a coefficient of 3 in front of the CO2. Coming back to the left-hand side, the number of hydrogens in propane is 8. So when we come to the right-hand side, that means we'll need a coefficient of 4 in front of the water, because 4 times 2 is 8. Now this is where you want to add up the number of oxygens that you have on the right-hand side of the equation and use that to work backwards and get your coefficient in front of your O2. So in the CO2 we have 3 times the subscript of 2 for a total of 6 oxygens, and in the water we have 4 times the subscript of 1 for a total of 4 oxygens. 6 plus 4 is 10, so now working back to the left-hand side, that means we need a coefficient of 5 in front of the O2. 5 times 2 gives us 10. So now we have balance from left to right in both the carbon, the hydrogen, and the oxygen. Okay, so part A in this particular problem, after you have balanced the equation, is actually asking you to calculate the theoretical amount of product that would be formed. And so this is a limiting and excess problem, and this involves a lot of writing for me to get both calculations up. So I'm just going to start by saying, remember that for these you start with both given amounts, so 2.00 grams of the propane, C3H8, and then we'll have one calculation with that, and the other starting amount of reactant is 8 grams of O2. So I'm going to go ahead and hit pause here for a second, and I'm going to complete all of the stoichiometry to calculating the grams of water, because it's asking about water in this particular question, not CO2, and then I'll start back up once I've filled it all in. So if you want to take a second and hit pause if you haven't done this one yet, and go ahead and fill it in, you won't have to wait for me to walk through all of the steps. So now you can see I've written in all the numbers for the stoichiometry, and I'm just going to review the general steps. So step 1 in both cases is where we're converting from grams to moles using molar mass. Step 2, the middle step in each one of these conversions, is the moles over moles step, which is where you're using your coefficients from your balanced equation. And the final step is identical in both because it's converting from moles to grams of the product that it's asking for, the theoretical yield. So once you get these two answers, 3.27 and 3.60, your true final answer is the smaller of the two, because the idea is when you have formed 3.27 grams of water, the reaction will stop because you will have run out of propane. So propane is your limiting reactant, and oxygen in this case is your excess reactant. And then the last one in this section, finally, part B, is what is the percent yield based on your calculation for part A. It says if 2.25 grams of water is produced experimentally, what is the percent yield? So the formula we want here is Ty, whoops, I'm sorry, just flip that over. Give me just a second here to erase this. Your actual yield, so AY, over Ty, your theoretical yield, times 100. So in this case, the actual yield was 2.25 grams, theoretical yield was 3.27 grams, times 100. Your percent yield is 68.5%. 0.8% Y.